Good afternoon, everybody. I have gotten a lot of feedback that the momentum and impulse questions were way harder than the explanation provided. And I think, in part, that what happened was the explanation was just about concepts and we didn't go over enough problems to really understand what those concepts were. I hope now to kind of go through some sample problems so that you can really think about and understand how all this relates. Fundamentally, though, the way that I explained it is how a college physics class works. I do want you to know that. They will kind of expect you to go over the concepts for you to kind of fill in the gaps yourself. I'm still here, though. You're not quite in college, and I will help you every step of the way. So when I look at this, here are the equations. This is actually the equation that I gave you yesterday. What the heck is going on with my mouse? That's terrible. I have to erase that. Okay, this is actually the equation that I gave you yesterday, right here. Force times time interval equals the change in momentum. So what they're saying is mass times velocity, but they're just talking about like the change in velocity, because obviously as an object moves, it doesn't always change mass. They very rarely will change mass. So the change in momentum really comes from the change in velocity. So changing, I'm going to just keep a few notes here to keep in mind because we're going to see this. So changing velocity changes the momentum. So V changes, P changes. Don't forget that momentum is simply mass times velocity. So these are the equations in the textbook. I didn't give them to you in this way. That just means that they could be vectors, so you can add them up like vectors. We don't care about vectors. That's why there's an arrow on top of all of them. Force is a vector, velocity is a vector. So all it's just saying is, so force equals the change in time, and then this guy, if you think about it, this is really just almost like how we got acceleration. You do the final velocity minus initial velocity. But for momentum, you just multiply it by mass. Mass times velocity is momentum. So all they're saying here is that the change in momentum is equal to the force times the time interval that happens. And I said yesterday that the force and the time were inversely proportional. So if you have the same change in momentum, if this is constant, if you have more time, if your time is bigger, that means your force is smaller. We cannot forget directly proportional, inversely proportional relationships. This is the key. This is the key to understanding the second physics classroom that people got really tripped up on. Understanding that if you have more time, you will have less force. If you have less time, you will have more force. So this sounds really abstract. I was thinking about this. Let me give you an example. If you're doing an egg toss, and I think we even talked about this before. If you are doing an egg toss and you're tossing an egg from person to person across a room, when you catch the egg, you don't want your hands to be still. You want your hands to kind of cup, and then as you first touch the egg, you want to cradle it down. What is happening? If you have one person who just catches the egg and the egg splatters because the hand stays still, versus another person who catches the egg, but instead of grabbing it, they cradle it back with their arms. So their arms go back like this. This egg breaks. This egg doesn't break. What is the difference between the two situations? And this is in essence what that second physics classroom problem was talking about. It said, when you have more time to stop something, you have less force. So this guy has more time to stop the egg, so therefore the egg experiences less force. This guy stopped the egg immediately. He stopped it in less time. So therefore the egg experiences more force. The difference is the egg breaks here and it doesn't break here. So that's the concept. Okay, again, I understand the value of going through problems like this together. So let's go ahead and look at the equations and the concepts together. The first one I gave you, which I feel like people were kind of able to do, this is the equations. The first one was the equations, the second one is concepts. So let's think about it. We know that P equals mv. Okay? So let's go ahead and figure out what our change in P is. Our change in P, or delta P, would be the difference from the initial to the final. Well, P equals mv. The mass is 2, the velocity is 2. So the P here equals 4. Okay? Here, the P, mass times velocity, 2 times 14 is 28. Okay? To get a delta P, you always do final minus initial. So the delta P is going to be 28 minus 4. We did this back when we did the triangles. So again, I didn't explicitly say this yesterday, but I did expect us to remember it, and that could be my bad. So P equals positive 24. So I need not just P, the delta P. The delta P here. That means the sum of these two things has to equal positive 24. Okay. All right. So delta P is the change in momentum. So we cannot forget that delta P has an equation that we just saw, which is F times delta T. I also said yesterday that the change in momentum is also known as impulse. Just definition, impulse. So when it says the impulse for this first one is plus 18, what we're saying is, okay, so that would change the momentum 18. Let's not forget units for now. Don't let units bother you. Okay, let's just figure out what the change in momentum is for this one. So what we are solving for in each of these is a delta P. All right, perfect. So delta P, 18. Okay, force delta time, multiply. 48 times 0.5, that's positive 24. That's the delta P. Force time, this is positive 12. That's the delta P. Oh, this was great. This one just gives us the delta P is 32. It just gives it to you. Great. But again, if you don't know what you're looking for, that's not helpful. We are looking for the change in momentum. That's what it says. To indicate the momentum change. That's what we're looking for. Now, impulse here is negative 8. Oh, impulse is delta P. No difference. Okay. So now we know what all the delta P's are. So which two of these combine, in which you add them up, give you a positive 24? So you can't just pick positive 24 because you need to pick two of them. Positive 24 plus anything else would not be positive 24. Okay, so, the smallest two numbers, 12 and 18. So if I add them up, that's 30. That's too much. So I'm going to need to use the negative. Okay, so this is just kind of like mental games now. What two numbers, what, and then negative 8 is going to equal positive 24. What plus what equals positive 24. Oh, check it out. Positive 32 and negative 8 together gives you a change in momentum total of positive 24. That's it. That's all we're doing here. I understand I may not have explained this fully last time, but hopefully this helps clear it up now. It's just simple math. Now, these are the questions that I believe are going to give you guys nightmares. We've got like pig level problems going on now. So it says, compare the collision between the two baseballs and a catcher's mitt. So I'm going to read case A. Case A says, a baseball is pitched at 40 meters per second and collides with a catcher's mitt and is brought to a stop. Okay, so it starts from 40. I'm just going to keep that aside, and it goes to 0. All right, so it's going to be a change in velocity, really the change in momentum. An identical baseball, meaning it has the same mass. Oh, sorry. The catcher's mitt with a relaxed arm and retracts backwards 30 centimeters as the ball strikes the mitt. Okay, cool. An identical baseball, same mass, is pitched at 40, okay, 40 meters per second, and collides with a catcher's mitt and brought to a stop, so it goes to 0. Okay, so because the masses are the same and the velocities are the same, that means the change in the velocity is the same, and because the mass is the same, check it out, the change in momentum is going to be the same. Okay? So the change in momentum is going to be the same. So let's think about it. Let's look at the questions. Which variable is different for these two cases? Well, we know it's not the delta V. It cannot be the delta V. It cannot be the mass. Let's think about it. If you hold your hand firm and stop a ball, it stops quicker than if you let your hand move with the pitch. So the difference is time. That's the difference between the two situations, is time. One stops it quickly, one takes more time to slow it down. Which one takes more time? Case A takes more time. You know that because it gives it. So when you read situations like, oh, I've run into a brick wall versus I've run into a padded wall, that's what I was trying to explain when I had the picture of the trampoline and the pillow and the water. All those things bring you to a stop, but the difference is the time that it takes to do that. Okay? So the second question, which case involves the greatest momentum change? Okay, so we already figured that out. Oh, the change in momentum is the same because they both start at the same speed and they both end at the same speed. Nice. Which case involves the greatest impulse? Impulse and momentum change are the same thing. It means, so whatever you have here is always going to be the same as you here. They cannot be different. Impulse and change in momentum are the same thing. So which case involves the greatest force? Now I said force and time were inversely proportional, meaning the one with less time is going to have more force. Which one has less time? That's it. Let's look at another. Okay. Compare these two collisions of an egg with the floor. All right. A jumbo egg is released from 1 meter height. It falls to the ground, it stops. Okay, so I know that I don't know what it starts off with, but I know it goes to 0. Okay. The same jumbo egg is released from a 5 meter height and falls to the ground and stops. Okay, they both end at 0. I could use the equations. Again, I'm trying to think of concepts. I could use the equations and figure out how fast they would be going. You know, I could use the d equals v naught t. I could do all of that and figure out exactly how fast they started. But it doesn't really matter here. Which one's going to be going faster? The one that started higher. So we know that the one that was dropped 5 meters is going to have a greater change in velocity, the one that was dropped from 1 meter. Okay? That's the physics. If something falls for longer, it goes faster. So we know that the change in velocity is not the same between these two cases. The change of velocity here would be more than the change in velocity here. So which variable is different for these two cases? Well, it says the collision time is the same. So it says time is the same. Same. It says jumbo egg, and then it says same jumbo egg. So if it's the same object, the mass has got to be the same too. Okay? So because these two are the same, the delta V has to be different. So sometimes if you can't quite figure it out, you can deduce it out. You only have 3 options for this first one, delta V, mass, and time. So if you know the time is the same and the mass is the same, you know it's got to be the delta V, the change in velocity. Okay, so which case involves the greatest momentum change? Oh, well, which one has a greater change in velocity? Clearly B. If I said, which I did, and I'm going to repeat, that which case has the greatest impulse, whichever one, change in momentum is the exact same thing as impulse. So they're both going to be B because they're asking the same question. And then which one involves the greatest force? Okay, well, let's think about it. So, if they are falling at the same time, I know you're thinking, your gut reaction is to be like, well, then they'll have the same force. And I understand why, but you could only say that if the momentum is the same. Think about it this case. Because the change in momentums, because the impulse is not the same, is it going to take more force to stop the faster object or the faster object or the slower object? Here's where logic needs to prevail. It's going to take more force to stop the faster object. If you don't get that and you want to see the math, here's the math. Let's just call these numbers our momenta. So we said mv equals ft. Okay, that's our equation. So we have 1 equals f. And it says the same time, so we'll just make up a time. We'll say f times 1. The time is 1. That's how many seconds it takes to stop. I know it doesn't, but it doesn't matter as long as it's the same. The other one momentum we're going to call 5. So 5 equals f times 1. I'm sorry you guys, my fault. So if you want to think about it in a mathematical way, because the momenta are different and the times are the same, if momentum and force are directly proportional, so if you have more momentum, you're going to have more force if the time is the same. So if time is the same, if time is constant, force and impulse are directly proportional. So I am relying on just a little bit of logic here. But again, if you can just understand the logic that it takes more force to stop a faster object, you're good. But I am kind of hoping that we can remember some of these things that we talked about before of directly proportional, inversely proportional, and be able to look at these equations and understand how they relate to each other. Don't overthink this. You can totally do it. I know it looks odd, but you have the skills. Data away. You got this.